So we just used the Gibbs free energy to predict whether a reaction is spontaneous or not. Now, those were under standard conditions. What we looked at were situations where we were predicting the reaction when we had everything under the correct control. Now, as we showed with the water self-dissociation reaction, delta G of reaction, delta G naught, that we calculate, is not necessarily the same as whether a reaction does take place to a more limited extent. So delta G of reaction is not necessarily the same as the delta G naught of a reaction under standard conditions. Water does not spontaneously boil. Water can have a substantial vapor pressure above. Water does not substantially boil at room temperature, but it still can have a substantial vapor pressure. So these can be calculated if we, instead of looking at the Gibbs free energy, we can look at the Gibbs free energy of a reaction under non-standard conditions. We can use the following. Delta G of the reaction is equal to delta G naught, standard conditions, plus the following quantity, RT ln Q. Now we've seen Q before. This is our reaction quotient, same form as our equilibrium constant. Looks the same. And it relates to this idea of the products over the reactants. We've already seen this in effect in terms of Le Chatelier's principle. Le Chatelier's principle says if we stack the deck towards one side of the reaction, we can get it to drive backwards or forwards depending on how we modify the presence of the reactants and the starting material. And this is directly mirrored in this equation. So what this allows us to do is predict whether a reaction is spontaneous. And by this I mean it allows us to plug in concentration values and see how that affects the spontaneity of the reaction. Will the reaction take place if there's a partial pressure of oxygen of 20 millimeters of mercury or what have you? What temperature will it burn? Will the reaction proceed? And it also allows us to vary the temperature. So this is very powerful. This is a very powerful equation, allowing us to utilize it. Additionally, we can also rely on the special case. That is, at equilibrium, delta G of a reaction is equal to 0. Delta G is equal to 0, not delta G naught. So what that means is delta G naught is equal to negative RT ln KEQ, allowing us, if we know the equilibrium constant, to calculate the delta G of the reaction, or vice versa. There's also the potential form. KEQ is equal to e to the negative, allowing us to use delta G information to calculate the equilibrium constant. So a lot of flexibility. Given an equilibrium constant, all of this stuff that we've been talking about for the past several weeks, it's directly tied to the free energy change in the reaction. How do we use this Gibbs free energy equation under non-standard state conditions? All right, so let's take a look at a problem. Estimate what the partial pressure of iodine gas is in equilibrium with solid iodine at 100 degrees centigrade. This is the prototypical hard chemistry problem. It's hard because there's no information present. I mean, we wouldn't even know, is it equilibrium? I mean, they mentioned this word equilibrium. Okay, no, they don't give us any concentrations. Normally we'd have to, so if we were having our equilibrium constant, Kp, well, the way we get about this is we'd find the equilibrium partial pressures, but we don't have that information. And so there's this absolute dearth of information. What they tell us, they have iodine solid in equilibrium with iodine gas. There's an equilibrium constant associated with that. We'll just call it Kp. In this case, Kp would equal the partial pressure of I2. Products over reactants. All right. So that would be, how would we find that? Well, we don't have any other information, but we know that delta G is equal to negative RT ln KEQ, or Kp in this case. At equilibrium, delta G naught would equal negative RT ln K. Again, we can sort of use this sort of non-standard state conditions and plug in that temperature and figure out what this equilibrium constant would be. So let's take a look at how this would work. We can go to our books and we can determine that the delta G of this reaction, delta G naught of this reaction, would be equal to the partial pressure of iodine, the gas, 19.3 kilojoules, minus the starting condition, which would be 0 kilojoules for iodine solid. Says that the delta G of this is 19.3 kilojoules per mole of iodine at standard state. So we can use that delta G, we can plug that in under standard state conditions and rearrange and solve. K is equal to E negative delta G over RT. Just as a rule of tip, the units for this have to be in joules because R is in joules per mole Kelvin. So this value K would equal negative 19.3 thousand joules divided by 8.314 joules per mole Kelvin at temperature of T 373 Kelvin. E raised to that power would be equal to our value. Equilibrium constant would equal, gives us K is equal to 1.982 times 10 to the minus third. So at that temperature, 1.98, the equilibrium constant would equal 1.98 times 10 to the negative third, which in this case would also be the partial pressure in atmospheres. So again, key aspects, equilibrium, and then a sort of dearth of other information implied. Gibbs free energy and our thermodynamics tables allow us to do almost anything related towards the determination of the equilibrium constant. In fact, we can estimate these equilibrium constants from almost anything, almost any values, which is very powerful if you think about it. It allows us to figure out whether a reaction even progresses at all under a certain set of conditions.